Okay, everyone. Hello. Welcome back. Microphone is working. Everything? Yes? Okay. All right. Welcome back. Happy Valentine's Day. I hope you're all enjoying it. Spending it in the best way possible. Let me remind you where we were last time. Last time we introduced the notion of higher form symmetries, which involve having topological defects or charge defects that live on extended manifolds that wrap other objects which are also on extended manifolds, okay? And so, for example, in the case of having a one-form symmetry in 3D, it looks really exactly like this. We'll have a line operator, and that will carry a charge which is measured by another line operator, a codimension 2 object, okay? These two objects are inextricably linked in that if I take this and I try to deform it so it does not cross this anymore, it's topological, but when it crosses the object it is charged under, the thing will pick up a phase. Okay, that was the main point of yesterday. Everyone happy with this? Okay, good. And then we started working out electromagnetism. And so this is just normal U1 E&M. The action of U1 E&M was just taken to be this, 1 over 4 E squared F squared. And then let me just remind you what I said last time. I pointed out that there are two one-form symmetries present in this theory. There is the electric one-form symmetry and the magnetic one-form symmetry. Okay, so 1 over 4 pi. I have run out of space on this board due to lousy planning, but you get the idea. There's an epsilon multiplying the F in this case. Okay. Okay. And last time we also pointed out that these things are both conserved. The conservation of this guy followed from the equations of motion of Maxwell E&M. And the charged object, so I should write down a little bit more notation. This is U1, 1 electric. This one is for one form. This one is for the one-dimensional phase rotations. And this is U1, 1 magnetic. Okay. And now the charged object under U1, 1 electric was the normal Wilson line that we all know about. What you do is you take the normal gauge potential A, you integrate it on some closed curve C. It's important here, this thing requires that C be closed, or rather not have any endpoints. That's really what I mean when I say closed. You integrate it over that, and then you get something. Okay, the charged Wilson line. And this, therefore, satisfies the Ward identity that we want, which I'm going to write in form notation, that in the path integral, an equation like this is true. The Wilson line of charge Q satisfies the Ward identity, meaning the electric current is not conserved in the presence of the line. If you hit the line itself, you get this delta function, which I defined last time. Okay, that was a quick summary of where we stopped last time. Are there any questions about this? Everyone happy with this? Okay. Okay, good. So now, what we're going to do now is talk about the magnetic current. Okay. So, sorry, I left out one more thing. The action of this U1, before getting into the magnetic, let me remind you of one more thing. The action of this U1 field is pretty easy to understand, this U1 electric symmetry. It corresponds to the shift of A by a closed one form. Okay? So this is how the U1 one-form symmetry acts on the vector potential. It shifts A by a one form which is closed. Okay? This clearly leaves the action invariant because that's just how it is. Okay? Okay. Now, and also under the symmetry, this guy WQ picks up a phase, so that again makes sense. It's a charged object; it transforms in a nice way. Now here's the question: suppose I want to couple an external source. B mu nu to this system. So remember when we started doing this, I introduced normal U1 symmetries, and I explained that it's possible to couple an external source to a given U1 symmetry. In that case, we had an external gauge field A mu. Now I should have an external two-form field B. So how do we do this? Let me point out to you what you do. So this semicolon is to just remind you that A is a dynamical field and B is an external source. Okay? And what you do is you couple it in the following way. Okay, and I'm calling this B electric because it's not the magnetic one, it's the electric one. So this is B mu nu E. Okay? So this is how we couple an external source to this guy. And what is the criteria for doing this correctly? The criteria for doing this right is that you get an enhanced symmetry, right? This symmetry is now enhanced in the following way. You get that you can shift A by a 1 form, and you also shift B by D of that 1 form, okay? Well, now this lambda 1 is actually arbitrary. We no longer have the restriction that d lambda 1 be 0, okay? So this is clearly a special case of this, right? If you couple in the source in the right way, as long as you transform your source, you can perform the transformation on the dynamical field by an arbitrary 1 form. And in the case where B equals to 0, it only works if you also have d lambda 1 equal to 0, okay? That makes sense to everybody on what we're doing here? It's again strictly analogous to the case for normal zero form symmetry. Okay. So that's pretty much all we have for the electric current. So now we're going to come to the magnetic current. Okay, so the magnetic symmetry. So now I seek an object so that when I compute the divergence of J mu nu magnetic in the presence of that object, I get a delta function in the right way. Okay? And we've discussed problems like this in the tutorials, right? This has an extra index, but we know how to solve this already. So what is the charged object? The charged object is called a 't Hooft line. Okay? So I'm going to denote a 't Hooft line by Tp of C. This capital T is for 't Hooft, I guess. And this 't Hooft line has charge P. It's also defined on a one-dimensional curve C. Okay? Now, the definition of the 't Hooft line is the following. We demand that in the path integral, we have that the integral of every small S2 wrapping C, we have that the integral of f is equal to 2 pi times p. Okay? So if you want to look at what a 't Hooft line does, what you do is you take your path integral, there's a curve C in this path integral, and you demand when you do your path integral that for every small S2 who wraps this one-dimensional curve, the integral of f through this small S2 is 2 pi times p, where p is an integer. It must be an integer, okay?
So are we in 4 Euclidean dimensions?
We're going to be in 4 Euclidean dimensions right now. Yeah, that's right. The case of 3 Euclidean dimensions we actually did yesterday during the tutorial, to be honest. Now we're in 4 Euclidean dimensions, and yeah, this 4 is actually quite important, all right? It's a good exercise to think about what happens if you play with the dimensionality, but for now we're in 4, okay? Okay, so this was sort of thing was discussed in tutorials already, but this is an example of a disorder operator. It is not defined as some sort of simple polynomial or exponential of fundamental fields. It is defined as a boundary condition on the path integral, okay? But having said that, this is a quite precise definition. Everything you want to do with an operator, you can do like this, okay? Now, physically, what is this thing? Physically, This is the world line of a test magnetic monopole. Okay. A Wilson line is the world line of a test electric charge. And this thing is the world line of a test magnetic monopole. Okay? So what you're really doing when you insert a 't Hooft line is you're saying, I am demanding that a magnetic monopole live its life along my curve C. What will that monopole do to all the other fields? Okay? That is what the 't Hooft line does for you. Yeah, sorry.
Can we then define Wilson lines the same manner just without that use star F?
Oh, that happens. Yeah, that happens. You don't need to do this crazy stuff though. Like what you can, for the Wilson line, it's easier. Just insert this, put this into your action, and it will be true that integral star F equals to 2 pi q. Yeah, that's just a fact. Yeah, but that's just normal. What you're just saying is the line creates electric field. That's it. Yeah, that's easier. Yeah. Okay, good. So let me just remind you about a few things about magnetic monopoles. You see. This formula, if you plug in F equals to dA into this formula, you get a nonsensical result, right? You get that integral of dA over some manifold with no boundary equals to something non-zero, right? That can't happen if A is well-defined. What that really means, of course, is that A is not well-defined when you have a magnetic monopole. And nevertheless, we work with A anyway, and there's a delicate balance of things that makes this all right? The fact that A is not well-defined, but you have to sew it together in patches using gauge translations and so on, gauge transformations and so on, is what gives what's called the Dirac quantization condition. Have people seen the Dirac quantization condition? Some people have, yeah. So if not, we can do this in the next tutorial. It's a classic thing. It's done in a lot of books. And this just tells you that the theory only makes sense if the electric charges and magnetic charges are both quantized. Okay? You require the following condition, that Q, the electric charge, times P, the magnetic charge, the product is an integer. Okay? I hope that I've done this. I tried to get the 2 pi's right here. I think I've gotten them right. Okay? But really, okay, I think it's right. But yeah. Okay. So, and this is, just to stress, this sort of thing only works in compact U1. If you're doing the non-compact group, as some people were asking about yesterday, you lose various structures. In the non-compact gauge group, you basically don't have magnetic monopoles, so you can't do this anymore, okay? The gauge transformation you need to make sense of this does not exist anymore in that case. Right. Okay, good. And now, finally, because this is a charged object for the magnetic symmetry, there is a Ward identity you can write down for it. I'm just going to write down for you what it is. The Ward identity is really the same as you expect from there. D star Jm in the presence of the 't Hooft line is not 0. It's I times P times the delta function times the 't Hooft line. Okay? And this statement here is the same as this statement here. Okay? So I'm leaving that for you as an exercise, but basically the point is if you take this thing, integrate this over the interior of this ball, and then use Stokes' theorem and transfer it to the boundary, and then stare at what you get, you'll see that you get exactly this formula. Okay? So this to this makes sense. It's very easy. And this to this, it's also true if you put the right restrictions on things and think about what a delta function means and so on. Okay, good. Any questions about this? Does this make sense to everyone? These are the two symmetries, and now we know the charged objects for the two symmetries. Okay, so now that we have these two things, what we should ask is, how are these symmetries realized? Okay, that's the next thing we should do. Whenever you have a symmetry, you should ask, how is it realized? Is it spontaneously broken? Is it unbroken? And so on. And we have all the formalism we need to do this. Okay, so we should ask, how are they realized? Yeah. Did it work? I was so proud of myself, I remembered. Yeah, okay. Okay. So how are they realized? And to do this, what we should do is we should compute the expectation values of the operators, the line operators, and ask, do they have a perimeter law? Do they have an area law? And so on. Okay. Let's start by computing the Wilson loop. Okay. In other words, I'm computing the following expectation value. Okay, let's do it for a circle C. Okay, so we're going to do it for a circle C of radius r, and ask how does this behave? Okay, and this is a completely doable thing, right? Because we're computing an expectation value in a Gaussian theory, in a free field theory. So this is completely doable, and it's an exercise in Peskin in chapter 9. So I'm not actually going to do it here. Everyone can imagine doing it. Let me just sort of sketch to you what happens. You have this exponential. And now you basically use the fact that it's Gaussian to sort of make e to the I qa can be written as e to the minus aa, basically. There's some formula like this that you can use. And then what this is really saying is you compute the two-point function of the photon across the line, and you kind of integrate over it in the right way. Don't take this formula too seriously, because I've not explained to you what, there's really two integrals over the curve here. And physically what's happening is that this two-point function is measuring the correlation of photons across this loop. Okay, and then you do some sort of integral. Now, the correlation of photons in this thing, it's pretty weak, right? The photons create some sort of power law decay. It goes like 1 over x to some power. AA goes like 1 over x squared, okay? And so basically, just to say this decays pretty quickly and nothing really happens, okay? So after doing this sort of work, nothing happens. Nothing happens from the photon talking to the photon here, but on the other hand, there are short distance singularities about the photon talking to another photon very close to itself, okay? And those short distance singularities result in something that goes like the length of this loop, because you get short distance singularities per unit length, but nothing else really happens, okay? So this is a claim, but you can do the exercise in Peskin chapter 9 if you want to verify this. And what you get is that there's some sort of UV divergence. Let me not call it that. Let me just call it minus m UV times the length of the curve. Okay, this is what happens at the end of the day. All right. Okay, so this is Peskin. All right. Okay, which means that this is a perimeter law. Which means that the one-form symmetry is spontaneously broken. Okay. So this is maybe not a completely obvious statement, right? What I'm telling you is that in the very first field theory that you've ever known and loved, there is a spontaneously broken global symmetry present. It's a one-form global symmetry, okay? Now, what does this mean? You see, an electric field line is not a heavy object, right? We sort of know this. It's very easy to make electric field lines. They kind of just sort of fluff around all over the place, right? You can't ever pin down one electric field line and say, look, here it is. It's sitting here, because it sort of is all very fuzzy, okay? And that's why, it's because they've condensed, the symmetry is spontaneously broken. Yes? Yeah. Yeah. Oh, sorry. The truth is, okay, good question. I wrote M, because I'm getting ahead of myself, but it's E that's broken. Yes, thank you. But let's now talk about M. Why did I write that down? Okay, that's just because I made a mistake, really. But you can now do the same thing for TP of C, for the 't Hooft line, okay? And okay, you get the same answer, okay? There are various ways to see this. I think one formal way to see it is to note that this theory has electric-magnetic duality. You can interchange electric and magnetic fields. There's a thing transformation you can do. And that switches everything. It switches 't Hooft and Wilson lines. And then after you do that, you can work in the new duality frame, do the same calculation, and get the same answer, okay? So this thing also has a perimeter law. And therefore, U1, M1 is also spontaneously broken. So magnetic field lines in this theory have also condensed, okay? whatever that means. Okay. So, okay, so that's fine. But now let's just think a bit more about the dynamical implications of this. You see, what I'm telling you is that the vacuum is in some sense full of some sort of condensate of electromagnetic field lines, and these are really just words, okay? What one wants is to get something useful from this idea. Now, for normal global symmetries, for zero-form global symmetries, we have Goldstone's theorem, which tells us that if you spontaneously break a global symmetry, you get a gapless Goldstone mode. All right? In U1 electromagnetism in 4 dimensions, described by that action, we also have a gapless mode, right? It's the photon. It's the thing that you use to see me right now. And so I claim that the reason why there is a massless photon is that when you have the spontaneous breaking of a one-form symmetry, you get a gapless mode, and in this case, the gapless mode is the ordinary photon. So for this to make sense, I should now prove for you Goldstone's theorem for higher form symmetries, right? That's closing the circle. So we're going to do that now. We're going to prove Goldstone's theorem for one-form symmetries, or for p-form, in fact. Yes? Yeah. Not really. I would say that there's 2 polarizations of the photon for different reasons, and it's just the fact that one Goldstone mode can actually spontaneously saturate. This counting of Goldstone modes and symmetries is a bit subtle. It turns out one Goldstone mode spontaneously saturates 2 spontaneously broken things. I think that's what's happening here. The fact that there's 2 polarizations is because it's a one-form symmetry, and basically as you go up in forminess, you get more and more polarizations. Yeah, that's all. Yeah. Excellent question. Yeah. Okay. Good. So, so now we're going to prove Goldstone's theorem for one-form, or for p-form symmetries, in fact. But the pictures I'll draw will be for one-form symmetries. Any other questions before we get into that? Does the philosophy make sense? Okay, so let's start by doing Goldstone's theorem. And I'm going to start by proving it for zero-form symmetries. You've all seen a proof for Goldstone's theorem for zero-form symmetries already, I think. I'm going to give you a new one. At least it was new to me. I think it's a simple one, and you'll see how this can be generalized easily, okay, to p-forms. So this is a maybe slightly more formal interlude, because I'm digressing from my discussion of a particular model to now talk about, oh, thank you. I'm so close, 2 out of 3. I'm digressing from my discussion of a particular model to talk now about generalities. So everything I'm saying now is going to work for anything, okay? And then I'll go back to E and M afterwards. This is a formal interlude, Goldstone's theorem. Okay. So first, this is for zero-form symmetries. And so what I'm telling you is from a paper of me and Diego Hoffman from 2018. I believe this is the fastest proof of Goldstone's theorem in general, though. All right. What's going to be different about this proof is that we're going to do it not using the usual Hilbert space language, but in Euclidean path integral language. So we're going to prove Goldstone's theorem for Euclidean path integrals. Okay. So Goldstone's theorem tells you when a charged operator has a VEV, meaning the symmetry is spontaneously broken, there's a gapless mode, the minimal ingredients we need are the definition of the charged operator, which, if you remember, is basically this. There is the following Ward identity. Okay? We're back in normal symmetry language, so I've placed a local operator at a point, all right? And I'm saying that I'm computing the divergence of J in the presence of that local operator, O of 0, and the Ward identity says that there's a delta function at this point, at the origin, okay? Okay. Now, let's take this equation and consider the following thing. I'm going to make a ball surrounding this. This is a Euclidean sphere. The ball has radius r, and I'm going to call this ball BD. Ball means, remember, the interior is included, okay? So I'm going to integrate both sides of this over the interior of the ball, okay? So I'm integrating this side over the interior of the ball, and I'm integrating this side over the interior of the ball of radius r. Okay, so what happens? On this side, I'm integrating a divergence over the interior of something, which means this is begging for me to use the divergence theorem to convert that into an integral on the surface, right? Okay? So let me do that. On the left-hand side, I use Stoke or divergence or whatever this is called. I guess in this case it's the divergence theorem because I've written it not using forms. To integrate this on the boundary of the ball. So what is the integral on the boundary of the ball? It is okay. So let me just tell you a bit about what this notation means. These thetas are just the angles on the sphere. Okay. So the boundary of this ball is this SD, and these are just angles on the sphere. Okay, it doesn't matter what they are. All right. Ni is the normal vector to the sphere. Okay, and I integrate Ji dotted into Ni all over the edge of the ball. Okay, this is normal Gauss's law stuff. Okay. And now how about the other side? On the other side, I'm integrating x over the interior of the ball. The delta function, this is an easy integral. I get I times q times O of 0. Okay? It just gives me 1. Okay. Is everybody with me so far? Yeah? Okay. So far, this is true in any theory, right? Okay, now I'm going to take the expectation value on both sides. Okay. So now what happens? The expectation value of O of 0 doesn't actually know about point. There's only one point in this thing. By translational invariance, O at the origin is the same as O anywhere else. So this is just that, right? Okay. Over here, on the other hand, there's something non-trivial happening. There's the two-point function of O with the current on the edge of this ball, which you remember is a distance r away. All right? Okay. So now there are two cases that I can study. Number one, the global symmetry is unbroken. That implies that the Vev of O is 0. Okay? The right-hand side is 0. The left-hand side is, I guess, also 0, but I can't really say anything else. Okay? So that's all. Symmetry is unbroken. I can't say anything useful with this, so I'm not going to treat this case anymore. That's all I can say. Can say no more. Okay. Now, imagine the symmetry is spontaneously broken. In that case, O is not 0, by definition of spontaneous symmetry breaking. But that means the left-hand side is also not 0, right? The left-hand side is not 0, and the left-hand side also does not depend on the radius of the ball, right? It doesn't because the right-hand side doesn't. So that means that the left-hand side is both non-zero and does not depend on R. Now, I'm doing the integral of a spherically symmetric object, the correlator of Ji theta. To make this a little bit more clear, let me actually bring this thing in here. Okay? I'm integrating a spherically symmetric object, the outwards pointing J, the two-point function of the outwards pointing J with O at the origin, over a spherically symmetric domain, and I'm integrating that over the sphere, and I'm getting a constant answer, which means that the volume measure from this integral must exactly cancel something coming from the other integral. In other words, I must have that ji of theta O of 0 goes like IQO and I divided by r to the d minus 1. Okay. This has to happen because when I integrate over the sphere, I get a factor of r to the d minus 1 from the sphere, and that has to be exactly canceled by this r to the d minus 1 so that the right-hand side can be constant. Okay? Okay, that's fine. But that means, remember, this point, ji of theta, is a distance r away from the origin. That means in the Euclidean theory, there exists a power law correlation. Okay? There's a correlation function that decays like a power law in the distance. It goes like 1 over r to the d minus 1. That's the definition of a gapless mode, or a massless mode. Okay? And that gapless mode is the Goldstone mode. Okay? Okay. Is everyone happy with this? This is, I think, the fastest proof of Goldstone's theorem. It's really a I said a lot of words, but it's really a two-liner. It's just that to that. Okay? That's really it. And it's sort of, this proof should remind you of the way we derive the 1 over r squared potential in electromagnetism, right? It's the same thing. You know what the integral is. You know it's constant, so it must go like 1 over r squared. It's the same thing. It's not a coincidence. It's the same idea. Okay. Okay. So this is equivalent conceptually. If people have looked in like Weinberg at Goldstone's theorem, it's the same conceptually. If you cut open this path integral, then you get sort of commutators of things, and those commutators are the same things. But this is just a very symmetric way of looking at it. So you get, I think it's a little bit simpler. All right. Is everyone happy with this proof? Yeah.
I think this is just a bit of law that I don't understand.
Yeah.
Can you just say a bit more about why the existence of a power law tells you that there's no gapless mode?
Sorry, there is a gapless mode. Yeah. This is really just the definition, to be honest. Like when we say massless mode, what do you mean? What you mean is that something is like massive fields contribute to correlation functions at large distances, like e to the minus mx. That's almost the definition of what it means to be a massless field. If ever you have something going like 1 over x to some power, that means you have a massless mode in the theory, right? It's just the definition of what massless means, I would say. Okay. Yeah, that's really all. Yeah. So you can check that the Goldstone mode theory that you have creates this correlation. It saturates this correlation in the right way. Okay. So this is Goldstone's theorem for ordinary symmetries. And now, of course, we can do it for higher form symmetries. That's going to be next. All right. The way I formulated it, you can kind of see it's going to be really, really similar. Just the pictures I'll draw will look slightly different. All right. Are there any questions before I do that? I run through that calculation? No. Okay. Okay. There is one new ingredient. It's not completely the same. I failed at this, but someone fixed it for me. Yeah. Thank you. Okay. So now Goldstone for higher form symmetries. So one more thing I'll say is, this is kind of, Goldstone's theorem, we're all used to it, but it's really kind of non-obvious, right? I mean, you just compute something really simple, like compute the VEV of some operator, and you know that if that VEV of that operator is non-zero, you know something about the spectrum, right? You know about the low energy spectrum of excitations. It's not obvious that this should be possible, you know, but it's really kind of a remarkable thing. Okay, so now for our symmetries, we're doing it for p-form symmetries. So it's really kind of the same, except now I'm going to use forms. So if you have a p-form symmetry current, then the Ward identity for a p-form symmetry looks like this. Okay, where C is a p cycle now. Okay, and J is a p plus 1 form. Okay. Okay, it's p plus 1 form. Let me not clutter this anymore. Okay. Now, the case of interest is going to be basically the analog of this one, where we are in a spontaneously broken phase. For this proof, let me just assume we are in a spontaneously broken phase to start with. It'll make life easier. So let me assume we have spontaneous symmetry breaking of this p-form symmetry. Then, by definition, we have that W of C goes like the exponential of minus m times the length of C. Okay. Now, when I say length here, it's length for a one-dimensional object, for a one-form symmetry. For a higher form symmetry, it's not length, it's the local volume of the thing. Okay, everyone, that's just what L of C means in this context. Everyone's happy with that? This is just easier if I just write L everywhere. Okay? So here, let me just emphasize this. L really means the P volume of CP. That's what L means. Okay. Now, I want to point out that this P volume is a locally defined concept. Right? It's a local thing, which means I can define a new operator, which I'm going to call W bar. W bar of C is the same as W of C, just with this bit stripped out. So I'm adding plus ML of C to W of C. So I'm taking this and I'm just canceling out this perimeter law behavior. Okay? This is a perfectly fine thing to do. This is just a C number, right? This is a number which is independent of the theory of everything. It's just a number. And I can always take my line operator and multiply it by local functional of the line. It's just a number multiplying this. It's a perfectly fine thing to do. It doesn't work for anything that's not a local functional, though, right? Like I couldn't do this for an area law. That would not really make sense because the area is non-locally determined. It's a very complicated thing. But this is a locally determined thing. So I can always do this to create a W bar. Okay? Does that make sense? Okay. Now, W bar is basically the same as W. It has all the same behaviors, all the same Moore identities. In particular, we have the following Moore identity. We have that D star J of X in the presence of W bar. You know, this piece goes on both sides the same way. It's linear, right? So you get the same Moore identity. You get IQ delta C of X, W bar of C. Okay. Okay. So now let's set up our geometry. It's the same idea as that. Let me take W bar of C to live on a straight line, okay? Or more generally a flat P manifold, a flat P plane, okay? And then I surround this by a P ball, okay? This is the interior of a ball of dimensionality P, all right? So in particular, that ball intersects W bar at exactly one point, okay? The dimensionalities work out so that they intersect exactly once. That's just how this linking thing works, all right? So this picture really is quite accurate, to be honest. It looks like this, just with more dimensions added, all right? Okay, and the boundary of this B ball is an S D minus P minus 1 sphere. Let me just write that down. I have some B ball, and the boundary of that is S D minus P minus 1. This is the S D minus P minus 1, and colors. The ball is the inside. Okay. Okay. And now, as before, we integrate over the interior of BP, right? Oh, excuse me, sorry. I made a mistake. This is not BP. This is BD minus P. Sorry, that's a fairly annoying mistake. Now these formulas are correct. So the boundary of a ball D minus P has one less dimension, so it's an SD minus P minus 1. So now it's correct. I lied earlier. Okay. Okay. This picture is right, though. Good. Any mistakes here? Nope, I think this is fine. So now I'm integrating over BD minus P. So again, that makes sense. I can now integrate over the interior of this. J is a P plus 1, P minus. Okay, I'm going to fail at this, but it's the right thing to be integrated over this. I should be able to do this. No, it's right. P plus 1, therefore D minus P minus 1, and then it's, yeah, okay, it does work. So now I integrate this over both sides, and what do I find? Here I have a B D minus P form, which is D star J of X. And again, this is X that I'm integrating over. Okay? And then I have again WC equals to integral over BD minus P times IQ delta C of x, W bar of C. On this side, I use Stokes' theorem to reduce this to an integral on the boundary, which is the SD minus P minus 1 form of star of j. This is a correlation function between star of j and this line operator. And on the right-hand side, again, I look at the geometry. This delta function only gets a contribution when the two objects intersect, and they intersect exactly once from that point right there. So I get, on the right-hand side, IQ times W bar of C. Okay? So this is using Stokes. And then again, I take the expectation value of both sides. Yeah?
Maybe I'm not thinking about symmetry, but if I take this picture go one dimension up,
Yeah.
then I have an intersecting circle.
Yeah, so let's go one dimension. So which, let's keep this picture and go one dimension up, meaning making this into an S2 instead of an S1. Is that the way you want to do it? Yeah, that's right. So now I'm in 4 dimensions. So I have a line. I have an S2 wrapping that line, and the inside of the S2 is this ball. It's a B3. Does that make sense?
Yeah, but now I'm intersecting twice.
No. This is the S2, right? And the interior of the S2 is like a 3-dimensional volume. The line intersects the interior of that 3-dimensional volume, not the outside of the S2. Does that make sense? It's the difference between this picture and drawing that. It's not that. It's this. Does that make sense? Okay. So formulas in this are actually kind of helpful, yeah, to be honest. Yeah. But, yeah. Okay. All right. So you always get 1. Yeah. Because it goes through the inside, not through the outside. Okay, good. Other questions? Make sense to everybody? Okay. And now we're basically done. Okay. Notice that if we are in a spontaneously broken phase, which we assumed we were, then I have taken off the full dependence, right, of this line operator. I have stripped off the interesting dependence, and therefore the expectation value of W bar C is not 0. Because W bar is basically 1 by construction, right? I took off its dependence. So this is not equal to 0, which means this is not equal to 0, but it must be independent of the size of this ball, is always the same number. So again, the integral over the edge of the sphere must exactly balance the correlation function of j with this line operator. And again, by spherical symmetry, what you conclude is that star of j on the edge, so on this SD minus P minus 1, with this line operator, must go like some number divided by R d minus P minus 1. Okay? Where it's R to the d minus P minus 1, because I'm now integrating over an S d minus P minus 1. Okay? And again, we have a power law correlation. You can see the proof is really exactly the same as for the zero-form Goldstone's theorem, just the objects are more extended and so on. Okay. So let me just remind you what we just found out. I want to, let's see, we're doing, okay, it makes sense for me to erase the boards, I think. We just found out, what we have just shown is that a perimeter law for a U1 charged for a higher form symmetry, for the charged object of a higher form symmetry, implies there's a gapless mode in the spectrum. Okay? All right. Now, I'm going to erase the boards. Are there any questions while I do this? Is everyone happy? Does everyone believe me about the higher form Goldstone's theorem? Yeah. Okay. Yeah, question?
Can you say something about the number of Goldstone?
You know, with this argument, not really. But what you can do is you can just start to write down the effective theory. We'll do that in a second. You can write down the effective theory that saturates the ward identity. And then that effective theory, you can use that to count the number of modes. I kind of feel like there should be a way to say something about the modes from this, but without writing down an effective theory, I don't know how to do it. Yeah, it's a good question. Yeah. The truth is, the effective theory approach is quite powerful, and I think that's the right way to do it anyway. So I'll say more about that in a second. This what? Sorry? This W bar? If you don't do that, it's a little bit annoying because you see when I said here that this was not equal to 0? If you don't have W bar, if you just W of C, actually the perimeter of an infinite p-plane is infinity, right? And so technically that's actually equal to 0. So you got to strip that off. And you can only do that if its full dependence on the kinematics is local. So that's the key point here. Does that make sense? Yeah. I was stuck on that for a while, to be honest. In the proof, that's really the only non-trivial thing. So this confused us for a little bit. Other questions? Okay, I'll do the rest in the break. Okay, so let me just write down in words what we just learned. Thank you. We just learned, okay. We just learned in words is that if you have spontaneous symmetry breaking of a p-form symmetry, of a p-form continuous symmetry, which really means it's U1 because of this abelianness that I told you about earlier, where spontaneous symmetry breaking means that the expectation value of the charged operator goes like the p-volume of the operator, of the p-volume of the surface in which the operator is defined, that implies there exists a gapless mode. Now, you should ask, what is the low energy theory that describes this gapless mode? This comes back to your question. Whenever you learn there's a gapless mode, you should ask how to describe it. And someone's going to tell you what the answer is. The effective theory of this gapless mode is a p-form gauge field. Okay. This is the effective theory of the gapless field, where BP is a p-form gauge field. All right. In particular, you can realize the charged operator, WQ of C, in terms of that low energy degree of freedom as the exponential of the integral of BP on this p-form CP. Okay? So you have a gapless mode, this p-form gauge field with this action, and you can realize the extended object in terms of that p-form in the following manner. Okay? This is the sort of universal information that is present when you spontaneously break a symmetry. You want to know what is the low-lying degree of freedom, how do you express things that you like in terms of that degree of freedom, and this is how you do it. Okay? So notice for the case P equals to 1, we then have a one-form gauge field, and we realize the Wilson line exactly the way that we know and love, okay? So for the case P equals to 1, we really just get normal U1 E and M with the Wilson line written that way, okay? With A being the electric photon, with BP, with B sub 1 being the same as A, which is the normal electric photon. Okay? This is what happens if you run the argument for J mu nu electric. Okay? Now, you could also run the argument for J mu nu magnetic. Everything looks kind of the same, but what you end up finding then is that it's the Toft line who is realized in terms of some fundamental degree of freedom, and you would then call the degree of freedom that you get, you wouldn't call that the electric photon, you would call it the magnetic photon. Okay? But the physics is the same. There's a duality relation that relates the two of them. All right? So the point I'm trying to make here is that a set of words that one could say is the reason why we have this sort of massless U1 P-form gauge field is always to be the Goldstone mode of a spontaneous broken symmetry. Okay? This thing will let you saturate that ward identity, and that's really what it does for you. Okay? Okay. Any questions about this? Is everyone happy with this? Okay. Yeah.
Yesterday we discussed the case of freedom elements.
Yeah.
You said that somehow
Yeah.
generalism should be confined.
Yeah, that's right. That's right.
That would imply that this symmetry is not broken.
That's correct. That's correct.
There should be no photon.
That's correct. That's correct. In the
No mass.
That's right. Exactly. Exactly. In the confined phase of electromagnetism, the one-form symmetry is unbroken. It has an area law, right? You stick a Wilson loop into a thing. It has an area law. It doesn't have a perimeter law, and it's unbroken.
Can you,
Yeah.
because in other dimensions we don't have this converting duality, can you break magnetic one and not the electric one or vice versa?
Yes. Yes. Absolutely. You can. We're going to discuss that next. Actually, that's the next thing. Yeah. We're about to break the electric one. Yeah. That's right. And I'll tell you how to break the magnetic one. Yeah. You can always imagine it. It's a little hard to implement sometimes in detail because we don't have good dynamical principles for describing objects that are higher than particles, to be completely honest. But you can imagine doing it always. Yeah. Good. Excellent question. Other questions? Okay. So we're going to change topics a little bit. So maybe this is a good time to stop. I'll just leave you with one thing. You see, at the end of this, if you think about the low-lying degrees of freedom that exist in nature, what are they? It's good to think about this. What are the exactly massless degrees of freedom? And so there's many of them. There's in the vacuum, there's light. In mediums, you have things like sound, spin waves, and so on. But they're actually, if you have a gapless degree of freedom present in a phase, at this point, I think it's always a Goldstone mode. I think I'm comfortable making that statement. It's always a Goldstone mode. With one exception, which I mentioned earlier, which is gravity. Okay? The graviton is gapless. It's a phase. I mean, you can deform things however you like. The graviton will stay massless. And that's the only one that I don't think I know how to realize is a Goldstone mode. So I think that one for me now stands out. This is why when I started lectures, I put gravity really far on the other side. That and other reasons as well, of course. Okay, good. Let's take a break. Let's meet again at I can't read the clock. 2:45. Let's meet again at 2:45. It's about 7 minutes from now, and we'll take it from there. Okay. Okay, everyone. I'm going to get started again. Welcome back. I think most people are here. Okay, so what we just discussed was a sort of global symmetry reason why the photon should be massless. And I argued this actually works for higher form gauge fields as well. If the charged objects have a perimeter law, where perimeter means that it depends on the local p volume, then you can run this argument and basically find that there's a gapless mode in the spectrum. Okay. Any questions before I keep going? Yes.
So, if we had a theory, so my question is, what's like the principles that we should follow in order to this effective theory? For example, if we had more fields,
Yeah.
and we could like contract the vector field with
Yeah.
others, like we would create actions that would have massless modes.
Yeah, so the principle really is you should write down every term you can write down so that it preserves the symmetry. You should write them all down, to be honest. Yeah.
Specifically, we are focusing the ones in the actions that would have the massless mode.
You should do that. If you want to describe the spontaneously broken phase, then you should do that because you know that there is a massless mode in the spectrum. In other words, if you write down an effective action, it does not have the massless mode, then either it will not have the symmetry, so the current will not be conserved, or if you compute the expectation value, then it will not have this perimeter law. That's what must happen. So yeah, you should write, I would focus on the ones with the massless modes if you're trying to describe this phase. That's right. Yeah. Good. Good. Other questions? Okay. Okay. So now, to be honest, this is all fun, but like I have spent like a lecture and a half talking about free E&M, which honestly, I mean, it's great, but we really know everything there is to know about free E&M. You just write down the equation of motion and, okay, you can talk about it for a long time, but that's kind of it. Okay. So I now want to move on to more interesting theories. So from now on, the theories are going to have more dynamics. The first thing I'm going to talk about is E&M coupled to matter. The next thing I'm going to talk about is SUN gauge theory. And then after that, I'm going to talk about sort of simpler gauge theories that are nevertheless less familiar, like ZN and Z2 gauge theories. Okay. Okay. So first, E&M coupled to matter. I think I'll go this way. Okay, so now consider the following theory. I now have not just a vector potential, but a charged scalar field as well. And the action is integral d4x 1 over 4 e squared f squared plus d phi dagger d phi plus v of phi dagger phi. Okay. And my scalar has charge q, which means that the gauge covariant derivative of my scalar is d mu phi minus iq a mu phi. Okay, so the usual u1 gauge covariant derivative. This is perfectly gauge invariant, but the question we should now ask is what happens to the symmetries? Okay, and the potential, which I've written down, it's important that it have at least two terms in it. Lambda over 4 phi dagger phi squared. Okay? In particular, I'm going to take this m squared, I'm going to tune it through 0, and stuff is going to happen, and we're going to talk about what happens when I do that. Okay? Okay. Now, this is, I think, all I want to say here. And now what we should do is we should ask what happens to the symmetry currents that we previously discussed. Okay? That's what we should discuss next. So this actually depends on the precise numerical value of the charge, Q. Remember I told you charge is quantized, all right? So it takes integer values. So first I'm going to talk about the case where Q equals to 1, okay? This is the simplest case. The minimal case, unit charged electric fields. Okay. Now, if you recall the, let me just put these here on the side. I'm just going to remind you what the currents were that we had previously. J mu nu E is 1 over E squared F mu nu. J mu nu M is 1 over 4 pi epsilon mu nu rho sigma F rho sigma, okay? Okay, so now, first, are the currents still conserved? That's the easiest thing to check. What happens to symmetries? Do they exist? If they exist, the currents must be conserved. So in the case where Q equals to 1, actually in the case where any Q, we have that the divergence of the electric current is just no longer 0, right? Its divergence was 0 before because we had no matter. Now we have matter. The equation of motion is d mu f mu nu equals to the current coming from there, right? So if you work out the equations of motion, what you find is that this is just IQ times phi dagger d mu phi minus phi d mu phi dagger, which is, I'm going to call J mu electric, okay? So this is just what you call the current coming from the scalar field, right? This is a gauged current that is coupled to a gauge field, okay? So it appears as the right-hand side of this equation right here. Yes? Yes, thank you, thank you. How do I minimally fix that? I have to erase at least 3 things. good. Excellent, thank you. Other questions or other errors? Okay, so this current is no longer there, and so what we say is that the U1 one-form electric current has been explicitly broken. Okay, it's just not there anymore in this theory. Okay, now let me just talk about what this means physically a little bit more. So first of all, if you remember, the physical content of this symmetry was that electric field lines don't end. That's of course no longer the case, right? Now we have electric field lines and they can end on charges, right? Charges create and destroy electric field lines, and so that makes sense. The charge electric field line now can be terminated by a charge, okay? So now electric field lines can end. There are three charges floating around that end them. Okay, that's fine. And there's another way to see this. There's a new kind of object that I can draw now, right? Previously, my Wilson line operator had to be a closed loop. That is no longer the case anymore, right? I can now have an open-ended Wilson operator. So what does this look like? This open-ended WC is take phi and then integrate the Wilson line on some curve leaving this phi, okay? So you might have something like this. Yeah, that seems correct. So I have some curve C, but now I have a Wilson line and some curve that comes along some curve C and then ends at some point x, okay? So say I take this end to infinity, so this guy goes off to somewhere else. This is completely gauge invariant, right? The Wilson line, the integral ends at x, so the Wilson line is not gauge invariant, and this is not gauge invariant, but the combination is gauge invariant. This is a fine thing to do. But once you can end a Wilson line, it cannot have a non-trivial charge under a higher form symmetry anymore, right? Remember, a non-trivial charge meant that there's some sort of non-trivial topological linking, right? There exists some sort of topological operator that links with this in some way and creates a phase. And that's a fine thing to talk about, but clearly if you can end this, I can just take this object and just pull it off the end, right, and take it away without, so there cannot be anything happening there. So the instant you can break your line operators, they are no longer charged under a higher form symmetry, okay? There's another way to see this. This is the same statement as this, to be honest, but. Okay, good. So we have lost the electric one-form symmetry, but we still have the magnetic one, right? The magnetic one is still there. The divergence of this is still 0. Okay? So now our question is, how is this symmetry realized? How is the unbroken, or not explicitly broken, magnetic symmetry realized? Okay? And now this theory has two distinct phases, actually. And we're going to study both of those phases, okay, and ask how this is realized in each phase. Okay. So there are two phases. And they depend. Is it okay? I thought I pressed it for once. Yeah. Yeah, exactly. To be honest, there is a bit of a delay in the change, right? Like I press it and then, yeah, anyway. So, yeah. Okay, so there are two phases now. What are the phases? The first phase, and it depends on this potential, right? So here I have a potential, and the sign of m squared determines two different phases. So let me first start with the Coulomb phase. Okay? In other words, what I'm going to do is I'm going to take m squared greater than 0. So v of phi, it looks like this, and has a single minimum. Okay? Okay. Now, in the Coulomb phase, I just have massive phi particles, right, interacting with E and M. This is the first thing you study in QFT. So we have massive phi particles interacting with E and M. And this is really the same as the previous case, right? Let's go to very long distances, very low energies. okay, go to very low energies. So energy is much, much less than m. In that case, you can ignore the phi particles, right? I mean, they're heavy. They cost energy to make. You won't really make them at energies less than m, right? So the point is, at very long distances, you can just ignore phi. You can integrate it out, as they say. And then we're back, basically, in free E and M. Okay? So what does that mean? That means, first of all, that the U1 symmetry, the magnetic symmetry, we can do the same calculation for the 't Hooft line. We get the same answer as before. This is still going through spontaneous symmetry breaking. All right? There's still a gapless mode. That gapless mode is still what we call the photon, because you can just ignore the phi particle completely. Now, there's something interesting happening with this guy, okay, the electric one. Because I told you this was explicitly broken, right? I mean, it's true, there is a right-hand side to this. But you see, if the phi particle is very massive, then this is almost always zero, okay? It will never really be active, okay? And what that means is that somehow the right-hand side of this is not dynamically important. What we say is that the electric one-form symmetry is emergent in the IR. Okay? It has emerged. It was not there in the microscopics at short distances. At short distances, you can see this thing, it will be active and do things, but in the IR it is emergent. Okay? So I want to say a few words about emergent global symmetries. For normal zero-form symmetries, it's actually quite rare to have an emergent global symmetry. Let's think about why this is. You see, for normal global symmetries, we have local operators that are charged under them. If you add those local operators to your action, they will break your symmetry. They usually exist. If you have a symmetry, there's an operator charged under it. For the symmetry to be emergent, what has to happen is that you have to add that operator to the action, but the operator doesn't matter at long distances. That's what it means to be emergent, which means the operator must be irrelevant in the sense of the normalization group. That doesn't happen that often. It happens sometimes, and when it does, it's really fun, but it doesn't happen that often. Okay? On the other hand, one-form symmetries are different because they're actually much harder to break. To break them, notice how we had to break the symmetry. To break this electric current, what we had to do was, I couldn't just really add a term to the action. I had to add a whole new set of degrees of freedom, these phi particles, and then tell them to do stuff to break the symmetry. It is in general much harder to break a one-form symmetry, and therefore it is quite common for one-form symmetries to be emergent in the infrared. Okay? This is a philosophical statement, but it is one that sort of helps you understand various phase diagrams. Does that make sense to everybody? Okay. Yeah.
So if you add a mass term, so say you're still in pure E and M, you add a mass term,
Yeah.
obviously you break the gauge symmetry.
You mean m squared, a squared, just like that? Yeah, so that doesn't, that's not really a very good thing to do, right? You shouldn't add a mass to a vector field in that manner. So when I presented it to you, I presented to you as a gauge theory, and that means you have to preserve the gauge redundancy, because that's not a symmetry, that's just a feature of the theory. So what you're saying is actually breaking the gauge redundancy, and therefore is a completely different game. Yeah, does that make sense? Yeah, exactly. Gauge invariant things are like, they don't exist. They're just a fiction of, sorry, gauge variant things do not exist. They're just a fiction of our imagination. Yeah, exactly. Yeah, good. Yes?
Maybe the same question.
Yeah.
How can you add terms without adding degrees of freedom?
Oh, I mean, in normal field theory, I do it all the time, right? Like, forget about the gauge theory. Say I just had like a potential like phi square for my real scalar field. Then there's a Z2 symmetry, and I can break it by adding phi cubed, right? This breaks the symmetry. No new degrees of freedom, but symmetry is gone. Yeah. In a gauge theory, it depends what you're doing, but if you want to do something interesting like this, you need to add, the reason why is because in gauge theory, typically you're actually trying to break this kind of symmetry, this kind of one-form symmetry. Yeah. But we should talk about some examples, to be honest. This last two sentences have really just been a sort of, this is the kind of thing that happens. They're not really rigorous statements, okay? But yeah. Okay, good. Other questions? All right. So, okay, that's one phase. And so this is a bit boring because it's really the same as the other one, okay? So let us now, therefore, talk about the more interesting phase. And the more interesting phase, of course, is the Higgs phase, right? In the Higgs phase, we now take m squared to be less than 0, right? So my potential now looks like this. And my scalar field is going to roll down here and sit at the bottom of this potential. In other words, my gauge charged scalar field is going to condense. And this is a very different phase. All right? So let's now talk about this. This is the Higgs phase. It's also called the superconducting phase, the same thing. A superconductor is exactly this. Okay, so I'm going to use the words somewhat interchangeably, Higgs or superconducting, depending on whether I'm channeling a high energy or a condensed matter insight in that sentence. Okay, so let's now talk about the superconducting phase. Okay. All right. So I'm going to write down a low energy action for this phase. So it's convenient to take phi of x and to write it as a modulus and a phase field. Okay. And now a low energy action for the Higgs phase looks like this. Actually, let me not write phi, because, of course, this is not in terms of phi. This is kind of schematic, to be honest, but you get the idea. Okay. Here, V naught is this distance. It's the bottom of the potential. Okay. That's what V naught means. It's the value of phi that minimizes the potential. Okay. So how did I get this? I took this and I plugged it into that action, and you can check that basically, if you expand things in powers of delta V, which is V minus V naught, then the leading term is V naught squared times the thing with the phase and the A. And then again, the field wants to be at V naught, so there'll be a mass term preventing it from going too far away from V naught. That's this term over here. And then I'm going to call that the Higgs mass because it talks about that curvature. And there's many other terms that I'm just not going to think about, but they're there. Okay, so this is the low energy action of this theory. Now, you've studied this in your QFT class, and you know that if you work out the spectrum of this theory, this is completely gapped, right? There are no gapless, there's no massless degrees of freedom. There's only heavy modes in this theory, right? We say the photon eats the Goldstone mode and acquires a longitudinal polarization, and there are therefore 3 vector modes. And then the Higgs also, the modulus mode is also there. It also has a mass given by this m Higgs. So no gapless modes. And what that must mean, of course, is that the one-form symmetry that I'm talking about, the magnetic one-form symmetry, therefore must be unbroken, right, in this phase. That has to be, because it's all gapped. So now I'm going to show you how it can be that this symmetry is unbroken. All right, so we're going to discuss next. Okay. So to understand the realization of the magnetic one-form symmetry, what we should do is compute the charged operator. In other words, we should compute, we should compute the VEV of the 't Hooft line in this phase and see what happens, right? This should not have a perimeter law, according to what I've told you, all right? Okay, so what are we asking when we say this? What I'm really saying is, I want you to take your Higgs phase, I don't know why I drew a line, I want you to take your Higgs phase and insert a probe magnetic monopole into the Higgs phase. That's what I'm asking you to do. That's what the 't Hooft line does. So viewed from like at a constant time slice, this magnetic monopole is going to try to make magnetic field lines, and then these field lines will do something. And I have to now figure out what they do in the Higgs phase. Okay? Now, the whole point of a Higgs or a superconducting phase is actually that it does not let magnetic field lines in. Okay, that is its role in life, is to expel magnetic fields. People know about the Meissner effect, right? The expulsion of magnetic field lines in the superconducting phase. And what that means is these things cannot actually just go into the medium. Something weird has to happen to them, okay? They really just don't want to, they do not want to be here in the medium, okay? So what do they do when you force them in anyway? Because by putting a magnetic monopole in, I am forcing them to be there anyway. And we should ask, therefore, what happens to them, all right? I'll tell you what happens to them. What happens is that they form a tight little bundle, okay? And that bundle is called an Abrikosov vortex, okay? So all the magnetic field lines end up being forced into a little bundle, which is called an Abrikosov-Nielsen-Olsen vortex, okay? That's what happens. And so I'm now going to show you how to see that from a little calculation. I'm going to derive the structure of this Abrikosov vortex for you quickly, okay? So I'll be a little bit fast, but I'll show you what happens. Have people heard of the vortex before? I think some people have, but not everyone has. Good. I'm going to just go into the guts of this and show you what the magnetic flux is doing in this vortex phase, okay? Okay. So what is going on in here? So this is, what I'm going to describe is called the Abrikosov, I worry I'm spelling these names wrong, Nielsen-Olsen vortex. All right. And it's basically a localized configuration of magnetic flux in a Higgs phase. So let's go to polar coordinates. All right. So in polar coordinates, I'm writing this down, d tau squared plus z squared plus dr squared plus r squared d phi squared. Okay. So in particular, what that means is that I'm going to have, for example, let me call tau, I'm in Euclidean, so it doesn't really matter, but let me call tau time, okay? And then I'm going to draw the z direction here, and then I have r moving out and phi going around, okay? This is cylindrical polar coordinates, all right? And now, what I want to do is, I want to try to put in a non-zero magnetic flux, okay? I'm going to try to insert some non-zero magnetic flux in the z direction, okay? Oh, sorry. In the z direction, okay? So I'm going to try to put in some magnetic flux pointing that way. And what that means is that Fr phi is going to be non-zero, all right? So what I'm doing is I'm searching for a configuration of the equations of motion of this theory where Fr phi is non-zero. Now, you can't just turn on, if we were in the vacuum without the Higgs phase, you would just turn on Fr phi. Is it? Weirdly, here it shows the middle. I think. Yeah, it's the middle, yeah. Okay. Okay, anyway. Fr phi, if we were in the vacuum, you see, what you do is you turn on Fr phi everywhere. You could just say, I have magnetic field everywhere, and that's fine. But in the Higgs phase, you can't do that. The photon picks up a mass, and that's exactly the kind of thing that's not allowed, okay? So if you want to get a configuration where this is non-zero, what you have to do is the following thing. You have to make the scalar field cooperate with this thing in some way. What you have to find is, you have to find a configuration where the phase of the scalar field phi is playing a double role here as the microscopic scalar field and the coordinate. It's going to become annoying in a second. Okay, theta is the phase of the scalar field. So what you need is you need to have that phase of theta winds around. Okay? In other words, you need a configuration where theta, if you look at theta, the phase of the scalar field at large distances from the vortex, it winds around some integer number of times. I'm going to take it to wind around once, okay? So when I say theta is equal to phi, that means if you're at some large distance, this thing winds around once, okay? You can make this any integer, but once is the simplest. Okay, now what is happening? If this theta winds around once, something very bad is happening at the origin, right? Theta is not single valued at the origin, and the theory doesn't like that. What it's going to do is, it is going to force the scalar field itself, the original microscopic scalar field, to vanish at the origin, okay? If you make it vanish at the origin, then this ill-definedness of theta is okay, because it's 0, and 0 has no phase, so that's all right. So because theta is ill-defined at origin, what we need is that v at the origin, the magnitude of the scalar field must go to 0. And also what you need is that v very far away from the vortex goes to its background value. Okay? So what's going on here, if I make a plot of these two fields, if I make a plot of the magnitude of the scalar field, it is 0 at the origin, and then it asymptotes back to some reasonable value. Okay? This will take place over some length scale, which is roughly set by this length scale. Okay? You have to solve an equation of motion. You can solve an equation for this. It's not a hard thing to do. But roughly speaking, the length scale over which this happens is the inverse Higgs mass. Okay? So notice that at the origin, so this, by the way, is v of r, the magnitude of the scalar field. What's happening is that at the origin, the condensate is destroyed, right? V equals to 0, the Higgs phase is destroyed, and you have like a little core where the vacuum reappears. And basically, you can trap your magnetic flux inside this little core. Okay? That's what's happening. So if you do a calculation of the magnetic flux, what you'll also find is the magnetic flux now sort of has the opposite behavior. The magnetic flux is all going to be trapped. Sorry, it goes to exactly 0. Okay? So if I make a plot of fr phi as a function of r, the magnetic flux is only non-zero at the origin, and then it goes away. Okay? So this is a configuration where you have magnetic field at the core of the vortex, and then no magnetic field out the rest of the time. Okay? This is called the Abrikosov-Nielsen-Olson vortex. This actually happens. You take a real-life magnetic field, you take a real-life superconductor and put a magnetic field into it, it forms a vortex lattice where the core, each of the things in the lattice is this. Okay? Okay. Any questions about this configuration before I proceed? Does this make sense? Okay. Now, what I now want to do is compute the total amount of magnetic flux. Okay. How much magnetic flux have I been able to put in here? So what that is, of course, is an integral of d2x fr phi. Yes, fr phi. Okay. Where this d2x integral takes place over this plane. You might think you have to solve the equations of motion to do this, but you don't have to, actually. Okay? Because this is a total derivative. It's the integral of fr phi over some two-dimensional thing. This is actually equal to the integral of a phi at an S1 at infinity. Okay? You can reduce this to a boundary integral. Okay? So now, what is a phi? Well, remember at infinity I had that theta was equal to phi? My action has a kinetic term which looks like d phi theta minus a phi squared. There's a term like this, right? D phi theta from there is equal to 1, which means that a phi must also be 1. Otherwise, this will contribute a huge amount to the action. Okay? So really what's happening is a phi will dynamically track until it becomes equal to d theta phi. Okay? That's the configuration that minimizes the action. And what that means is at infinity, a phi at infinity is equal to 1. And therefore, this thing here is equal to 2 pi. So the amount of flux inside the vortex is 2 pi. Okay? This is a quantized number. It's always going to be a multiple of 2 pi. If I made this thing wind around twice, I would have gotten 2 pi times 2, and so on. This is not continuously tunable. Okay? So notice how different life is, right? Before I had a magnetic field, it was fluffy, it was going around. You're going to put some flux here, you can put how much flux you like. Now you can't. Now you try to put your flux in, it makes a tight little bundle. There's 2 pi units of flux in the bundle. That's it. All right? This is very different. This is really the point of the Higgs phase. Okay? Okay. So now let's come back to why. So any questions about this configuration? This is all quite fast, but it's a good exercise to go through this and solve the equations of motion yourself. And finally, let me point out that the core of the vortex, here I drew a picture at a fixed tau, and the vortex extended in z. It will also extend in tau. Okay? So the vortex extends in tau and z, and is therefore a 2D world sheet. World sheet in space-time. Okay. And it has a tension. It has a heavy tension. You can calculate the tension. It's some function of mh, and to be honest, it depends on the other couplings as well. You have to do some numerics to calculate the tension, but you can calculate it. It's a set of ODEs as a function of r. You can solve them with a computer, calculate the tension, and so on. Okay? Yeah. Yeah.
To be honest, I don't really understand any of that argument there. So,
Yeah.
what's the two-dimensional thing that you're integrating over?
Very good. So what I'm doing is I'm integrating over, I should just make this clear. These two dimensions are dr and d phi. Okay? So the reason is the vortex extends in z and in tau. I've not drawn tau. And so the amount of magnetic flux trapped in the vortex is something you get by integrating over the two transverse dimensions, so dr and d phi. Okay? And then, honestly, this is really pedestrian. This is dr a phi minus d phi ar, and ar doesn't depend on phi. So this just becomes this binormal calculus, actually. Yeah. Okay, makes sense? And I was a bit fast here. The point here is just that this is a term that appears in your action. You want to minimize it. Okay, you minimize it. This is equal to that, and d phi of theta. D phi of theta is just 1 because the field is winding around once. Okay, that means a phi is also 1 at infinity. Okay. Any other questions? Yeah. So there's a fair amount of, I tried to just really go very quickly to something that's actually, to be honest, deserves its own, like it could take half an hour of lecture easily, which I've not done for you. The point is just that Higgs phases, superconductors, they expel magnetic fields. If you force one in anyway, then it will form a bundle. That's really the point of what I'm saying. Okay. Okay. Now, now to come back to our initial problem, we started doing this because we put a pro-magnetic monopole into our theory. Okay. So you should imagine tau comes out of the screen here, and z is this way, okay? What I've told you is the magnetic monopole is going to make a tight little bundle of flux. That bundle is going to go as far as it needs to go. So if it's happy enough to find an anti-monopole, it'll stop there. If there's no anti-monopole, it'll just go on forever, okay? So now with this picture in mind, let us now go back and calculate the expectation value of the 't Hooft line. That was how we started, remember? So the expectation value of the 't Hooft line over some closed curve C. So here's my closed curve C. What is going to happen? The 't Hooft line makes magnetic flux. That magnetic flux makes a two-dimensional world sheet in space-time. Thank you. Makes a two-dimensional world sheet in space-time. Okay? So the flux forms a vortex. The vortex is a world sheet S, okay? And the boundary of the vortex is, of course, exactly this curve C, okay? This vortex is very heavy, it has a tension, and therefore the expectation is going to go like the tension of the vortex times the area of the world sheet, which is, of course, the area bounded by this curve C, okay? So the point of this is that in a Higgs phase, the 't Hooft line has an area law. And as I claimed earlier, this U1 symmetry is unbroken in this phase. Okay? This is the global symmetry way to think about the Higgs phase of electrodynamics. It's the phase where the magnetic symmetry is unbroken. Okay. Now, this might seem backwards to you, right? Like when you first learn about the Higgs phase, this is when I first learned about the Higgs phase, people say things like this. Well, you have a gauge symmetry, and then the gauge symmetry is spontaneously broken in the Higgs phase, right? And now I'm saying something the other way. I'm saying there's a certain global symmetry who is unbroken. There may seem like there's some tension here. So I just want to say, to be honest, this statement that the gauge symmetry is spontaneously broken actually doesn't really make that much sense if you think about it hard, right? Like, you know, what does that mean for the gauge symmetry spontaneously broken? If someone tells you a symmetry is spontaneously broken, you should ask them, okay, what is the order parameter for the gauge symmetry? And they might say something like, well, it's phi. You know, phi condenses, it's non-zero, but it can't be phi because phi is gauge variant, it's gauge charged. So phi does not exist. And then they'll be like, okay, well, no, never mind, I didn't mean phi, I meant something different. You might think, oh, well, let me take, okay, phi is bad. How about phi dagger phi? Phi dagger phi is gauge invariant. That seems like a good order parameter. But actually it's not, because you see, phi dagger phi, it doesn't carry any charges, and in fact, phi dagger phi is non-zero in both phases of the theory. It's just you have to do some quantum field theory stuff to see it, okay? Classically it's not, but quantum mechanically phi dagger phi is actually always non-zero. Okay, and never mind, I'll come up with something and they go away and they think about different things. And at the end of the day, a lot of people come up with this. It's just, you can arrive there directly by just asking what is the global symmetry that's present, okay? So I think this is the cleanest way to think about the Higgs phase, although of course all the actual predictions are basically the same as what you already know. Okay, any questions about this? Make sense to everybody? Okay, good. So I still have 20 minutes left, so let me just summarize everything that we've learned in a table. Yeah, I think I'll need to make a big table. And then I can start non-abelian gauge theory and get maybe halfway through. I think one of the big boards is probably enough. Okay.
Sorry?
Yeah.
You just said that I is not a good order parameter because it is charged?
Yeah. So phi, the scalar field that I just raised the action of, that phi is charged under a gauge symmetry. And so you cannot really talk about it. Like it is not possible to calculate the expectation value of phi, the gauge charged field. Okay? Because things that are charged under a gauge symmetry don't really exist. So for that reason, it's not a good order parameter. That's right. Yeah.
Because usually I would expect,
Yeah.
if I want to find an order parameter,
Yeah.
to recharge the symmetry so I can
Yeah.
have this.
That's right. It's important that you find something that's charged under a global symmetry. Only that makes sense. Things charged under a gauge symmetry, those are sort of fictions. You can sometimes calculate with them, but even then you've got to be careful that you fix your gauge and so on. Yeah. So that's right. So you cannot. The expectation value of a gauge charged object is basically always 0. It doesn't really exist. Yeah. Good. Okay. Other questions? Yeah. So the point is really just make sure you're talking about a global symmetry when you're talking about symmetry breaking. If it's a global symmetry, everything will make sense. If it's a gauge symmetry, it might not. Okay, so let me just summarize everything we just learned about E&M. Okay. So I'm going to make a table. This is a sort of table I really like to make. In the table, I list all the symmetries and all the phases, and I explain what they're doing in each phase. So this is the first of them in these talks, but I think happily I'll get to do at least one more. Okay. So there are two one-form symmetries present. So the first theory we talked about was free E and M. Okay? And in that case, these were both spontaneously broken, as we saw today. Next, we talked about having electrically charged matter. So this is the scalar field example. Oops, electric phi. And the first thing I discussed was when it was massive. If you recall, it's massive and long distances. You can basically go back to this phase. And then I argued this one was emergent in the IR. And this is the same. It's spontaneously broken. And then the other case you could consider is the Higgs phase, right? Where you condensed phi, where it's not massive, where it condensed. And over there, this is just explicitly broken. I'm just going to write broken. It's just not there at all. And this is unbroken. Okay? Okay. So now, because we have electric-magnetic duality, you should ask, what would have happened if I had coupled not electrically charged matter, but magnetically charged matter, right? You can imagine doing that. It's not a big deal. And then what happens if you had magnetic matter, then we can obtain the table through flipping, right? We would have found that this one is spontaneously broken, and this one is emergent in the IR. And then the name that we give to this phase is the confined phase, okay? Because if we had looked at a phase with a magnetically charged matter, where the magnetic monopoles had condensed, we would have found, let me just finish this table, we would have found that the electric one-form symmetry would have been unbroken, and the Wilson loop would have had an area law. And the name we give to that is the confined phase, okay? So the Higgs phase is the electromagnetic dual of the confined phase, all right? And the electromagnetic duality just flips this table around, okay? This is what you can have in theories that are called E and M, basically, all right? In the class of E and M type theories. Okay, all right, make sense to everybody? Yeah.
Can you just explain again the reason why the electric symmetry is that after when it is emergent, then it is spontaneously broken?
Okay.
Why that doesn't happen like with zero form symmetry?
Right, okay. So this is a bit philosophical, but basically it's a fact that if you have massive matter and you go to long distances, you can basically ignore the matter, right? That's just a fact about a dynamical fact. And therefore, if you have massive matter and go to long distances, you basically end up in this phase. I say it's emergent because you have to go to long distances for that. At short distances, you will create the phi particles and they will mess up the symmetry, okay? That's what emergent means here. Now, it's emergent and then it's spontaneously broken because really this is what's happening. It's emerging and then you're going to here at long distances. So it's emergent and then spontaneously broken. Now, the question you asked was, why doesn't that happen for normal zero-form symmetries? And it is a fact that it does not, and at least it doesn't seem to happen very often. And the reason is that what you should imagine asking is it possible to break a zero-form symmetry in the UV and have it emerge again in the IR? That means there's some sort of low-energy effective description of the theory where even though it was possible to add an operator that is charged under the symmetry to the action, it doesn't matter, okay? And normally we say such an operator is irrelevant. It's irrelevant in the RG at long distances. And normally charged operators are not irrelevant under RG. That's just a fact, okay? Now I keep saying normally because I can think of examples where this is not true and then you do emerge zero-form symmetries in the IR. But it's not as common as one-form symmetries. One-form symmetries emerge in the IR all the time, okay? So, yeah. That was a bit fast, though. I'm happy to talk about this more in the tutorial. The truth is, I should do this correctly. I need to introduce some machinery of RG and so on, which I've not really done properly. But I can do this a bit in the tutorial, maybe. I'll explain. Yeah. Does that sound helpful? Yeah. Okay. Good. Any other questions? Okay. Okay. So I now want to move on to, yeah, was there a question? Sorry. Oh, yes, sorry. Missed it. Yeah. That a symmetry emerges. If you look at, for example, large n QED in 3 dimensions, this is getting very specific. If you look at large n QED in 3 dimensions, so couple QED in 3 dimensions to n charged scalars, okay, then that theory has, in principle, it has a symmetry that looks like a current that looks like this. J mu equals to epsilon mu nu rho, F nu rho. Okay? And now, it turns out that this actually happens in condensed matter systems, except that in that case, the symmetry that you get here is explicitly broken on the lattice, by lattice effects, okay? But if you look at the CFT description at long distances, then the dimension of the lowest operator that breaks the symmetry, that dimension turns out to go like n. So if n is bigger than 3, it goes like n at large n. So if n is big enough, then this operator will be irrelevant. And then therefore the symmetry emerges at long distances, okay? This is an example, basically. It's a matter of a huge controversy, what happens to this at small n? Because then we cannot theoretically calculate it, and the lattice people keep simulating it, and it's a big and interesting story, but that's an example, okay? But this is a bit, I had to say many words to get there because this is a bit of a contrived situation. But that's all, yeah. I'd say generically it does not happen, yeah. Here you have to go to large n for it to happen. Good. Okay, any other questions? Okay, so I don't really, let's see. So if you remember, I took the charge q to be equal to 1 when I started this. It is fun to think about what happens if q is not 1, but some higher integer. Maybe you'll make this an exercise, because I want to get to non-abelian before I have to end today. But everyone, think about what happens if q is not 1. Say q is 2. What is the structure of the surviving symmetries? Okay, it's a little bit different. I'll ask you about it in the exercise. And for now, let's go beyond simple theory. So everything I discussed was a very simple theory. I will now go to non-abelian gauge theory. Okay. So, in particular, what is the phase structure of SUN? What is the higher form symmetry structure of SUN gauge theory? That is now what I want to ask. Right? So we're going to start with pure SUN gauge theory. So pure SUN Yang-Mills in the continuum. You'll see why I'm saying that in a second. So pure Yang-Mills in the continuum. And again, let's do 4 dimensions. This is the physically relevant case in 4 Euclidean dimensions. And the continuum action is S, which is a function of a non-abelian gauge field now A, equals to 1 over 2g squared, integral d4x, trace of f mu nu, okay? Where this f is the non-abelian field strength, okay? So just to be clear, A is A equals to A mu, sort of dx mu TA. So A is valued in the Lie algebra of the gauge group, okay? So, and it has a one-form index as well, of course, okay? So, in fact, that statement probably needs a little bit of clarification. So, A is in the algebra, right? A is in the Lie algebra. Which, when I have to write about it, I'm going to write it with, this is a lowercase SUN as opposed to an uppercase SUN. So this is the Lie algebra of SUN. Now, so I don't know why I wrote it like that. A is in the Lie algebra. It's a space-time valued element of the Lie algebra. Now, therefore, notice that the action actually only knows about the Lie algebra, right? But you can imagine different gauge theories with different gauge groups of the same algebra. This is a possibility, okay? It turns out the things I'm going to say are actually different for these different gauge groups. To specify a gauge theory, you have to say not only what the Lie algebra is, what the action is, but also what the global form of the gauge group is. So for example, I'm going to talk today about the gauge group SUN. The gauge group SUN is not equal to, for example, the gauge group SUN mod Zn, where this Zn acts by an element of the center. I'll explain this in great detail soon. But these are 2 different gauge groups that look kind of similar. They have the same Lie algebra, but they are different gauge theories. In particular, the things I'm about to say about higher form symmetries will apply here and must be modified here, okay? For interest of time, I'm not going to tell you this side. I'm only going to tell you this side. But just be aware that the global form of the gauge group is really important for all this stuff, okay? Okay, so with that caveat out of the way, I now want to start telling you some things about what the one-form symmetries are for SUN gauge theory. Okay? So, it turns out, so here's the statement. I'm going to make the statement that I'm going to prove it. it turns out that pure gauge theories with gauge group G have at least a one-form symmetry given by the center of G. Okay? And I'm going to denote the center of G by Z of G. Okay? Let me remind everyone what the center is. So the center of a gauge group G is the set of little g in big G such that GG prime equals to G prime G. Okay? In other words, the center of a group G, sorry, I should say what G prime is. I messed that up. Tried to be all mathy. For every G prime in G. Okay? In other words, the center of a group G is the set of elements that commutes with everything in G. It's like okay, that's all it is, yeah. The set of elements that commutes with everything in G. So what I'm saying is, pure Yang-Mills theory with this gauge group have a one-form symmetry given by the center, all right? Notice by construction, the center is obviously an abelian group, right? So there's no obvious contradiction at this point. Okay, good, first point passed. And now I have to prove to you that this is true, all right? So I'm going to do this in a bunch of steps, all right? So what I'm first going to do, wow, I thought I would not need so much board space. How am I doing? Okay, it'll take 5 more minutes. Let's see. Sorry, give me a second. I won't say too much more. I'll just introduce the objects, but I won't prove to you that it's true. Okay. So let me just first remind you for concreteness what the center is for SUN gauge theory. So I'm mostly going to talk about SUN. For SUN, the center is this. The center Z of SUN is Z sub n. Okay? And the way to see this is, I mean, if you just write it in a matrix representation, consider the following matrices. E to the I 2 pi k over n, e to the 2 pi I k over n, blah, 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 e to the 2 pi I k over n. Okay? So this matrix, where k is taken from 0, blah, 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 up to n minus 1, this matrix is unitary. It has determinant 1 because if you take a determinant, you multiply all these things together, and the n, you get rid of the n, and you therefore get e to the 2 pi I k, which is 1 because k is an integer. And it clearly commutes with everything in SUN. Okay? So these matrices, they're all diagonal, generate the center of SUN. Okay? So the center of SUN is Zn, the cyclic group on n elements. Okay. And so therefore what I'm saying is that pure SUN gauge theory, so pure SUN Yang-Mills, has a Zn one-form symmetry. Okay. Now, to prove this to you, I have to give you 2 things, right? I have to give you the charged operators under the one-form symmetry, and I have to tell you which are going to be one-dimensional objects, okay? It's a one-form symmetry. And I have to, almost more importantly, give you the topological codimension 2 objects that measure that charge, okay? So I have to give you some line operators who are charged and some operators to measure the charge. And then I have to prove to you that those 2 things have a Zn linking algebra. That's what I have to do now. Okay? The discrete symmetries are a little bit harder, in my opinion, than continuous ones because you can't just look for conserved currents. You have to really get into the guts of the theory and what is happening. Okay? That's what we're going to do. So the last formula that I'm going to write down is tell you what the charged line operators are. And everyone knows what they are already. They are Wilson lines. Okay. So a Wilson line in non-abelian gauge theory is defined by taking a trace over some representation of the gauge group of the path-ordered exponential of the integral of A over some closed loop C. Okay? Here R labels a representation of G. Okay? This is a Wilson line in non-abelian gauge theory. It can be defined for any R. Okay? It turns out that the charged ones, the ones that we want, is when R is in the fundamental representation. Okay? I'm just going to write R equals to F from now on for fundamental. It turns out you want to take it in the fundamental, then it's charged. Okay? It is not charged for all choices of R. If we take R in the adjoint, it is not charged under the symmetry. Okay? And for other representations, I have to think about it, but you can figure it out easily. But it is true for R in the fundamental and not for R in the adjoint. Okay? Okay. So that's the charged object, but this is meaningless, and you can sort of guess that maybe because you know about area laws and confinement and so on. The Wilson loop is going to be important. But really the dynamical statement comes maybe not from this, but from the topological object. The topological object tells you there's a conserved quantity that's important. So next I have to tell you what the topological object is. Okay? And this thing is called a Gukov-Witten surface operator, and we will construct it next time. Okay? Okay, that's all for today. Thank you.